Hello, everyone. Thank you, Dr. Johnson, for the invite to give today's extension talk by video. My name is Wang. I am assistant professor and state extension specialist working on sustainable vegetable and potato and vegetable production here at the Department of Horticulture, University of Wisconsin-Madison. Today's talk will be focused on the efficient irrigation management practices for the production of potato crops. Firstly, let's just quickly go over some background information about the irrigation management of potatoes. Sustainable agricultural production always requires more efficient use of the irrigation water. In some states of the US, there is a challenge of sufficient irrigation water in the areas like California because of the ongoing drought. Due to climate change, there are more and more water bodies for the surface water or groundwater that dries up and cause great attention by the agricultural industry to more sustainable management of the use of irrigation water. And on top of that, there are more unprecedented extreme weather conditions, like in the extreme heat that can cause an increased peak crop water use and evapotranspiration during the growing season. And this increased ET is also calling for more water or more efficient use of irrigation water. So all of those information boils down to the point that we need sustainable irrigation management. But what does it mean? In my mind, sustainable irrigation management is composed of two factors. One is we have to make sure our irrigation system is highly efficient. And also, we need to be smart about irrigation scheduling. When we talk about the use of irrigation systems, we have this common center pivot or linear move pivots. But we also have some new technologies, such as the variable rate irrigation, that can help us to increase the irrigation efficiency. Coming to the irrigation scheduling part, currently there are three common ways to schedule the irrigation events. The most common is to just fill the soil by hand. A second approach is to use a crop evapotranspiration and refer to that number for the crop need for water on each day. Or we can use different soil moisture probes to tell us what is the status of the soil moisture so we can adjust the irrigation based on that information. Doesn't matter if we're talking about irrigation system or irrigation scheduling. Nowadays, the new technologies are always going to be important for us to improve the irrigation efficiency. So here are some basic knowledge about irrigation management. Let's just quickly go over this graph. We can see that there is a line here showing the field capacity, which means the maximum amount of water that a soil can hold against the gravity. Field capacity is what we can maximally have in the water without causing any saturation. Beyond the field capacity, the soil will be saturated. All the pores in the soil will be full. There will be no space for air. So, and any extra water will be called the gravitational water that can flow through the soil profile down to the groundwater table. So we definitely do not want the saturation for managing the irrigation. Below the field capacity, we have this management allowable depletion zone. And this means the lowest moisture level that can be sustained by the crops without causing any adverse stress effects. So the management allowable depletion, or MAD, is what we want to target for our irrigation management. We do not want to have our soil moisture lower than the MAD level. If we, for some reason, leave the soil to dry up, and the soil moisture content will be, keep decreasing, then it will reach to a point where the plant water deficit will begin. And if the soil keeps drying up, the photosynthesis will start to slow down, and then it will reach to a point where the plant will permanently wilt and possibly die. And that's called the permanent wilting point, which is the amount of water in the soil that most crops growing in that soil will no longer be able to exist and extract water. We never want to reach to this permanent wilting point. The level or the available soil water between the permanent wilting point and the field capacity is what we are looking for, and they are called the total available water. Anything below the permanent wilting point in the soil is called unavailable water. So just to recap, when we're managing the irrigation for potato crops or any other crops, we always want to make sure that the soil moisture is within this management allowable depletion zone. We don't want to over-irrigate so that the soil moisture is higher than field capacity, but we never want to leave the soil too dry that the plant water deficit will kick in. So here is a good example of a good irrigation management. The red line here indicates MAD, and then the green line indicates the field capacity. The dark red line indicates a wilting point, the permanent wilting point. We can see that this grower managed his soil moisture pretty well. His soil moisture fluctuates between the MAD and field capacity with a really uniform, nice spikes. This is what we're looking for, because for potatoes, it's always good to deep water instead of shallow water. Deep water means that we want to give them a decent amount of water per irrigation event so that there is sufficient water in the rooting zone for the potato plants to uptake. So this grower did a really excellent job managing his soil moisture. In comparison, this is another example showing a poor irrigation management. When the soil moisture has a very random fluctuation, and below the field capacity, but sometimes the soil moisture content dropped way below the management allowable depletion, meaning that the plant will start to have some water deficit or water stress. And this occurred to the crop a couple of times during the growing season. And my guess is that the yield will be really penalized just because of the poor irrigation management. So just based on those two examples, we can tell that efficient irrigation management is really needed for us to keep uniform and consistent soil moisture within the rooting zone for the potato crops. So I mentioned there are two major parts for managing irrigation systems versus irrigation scheduling. First, let's spend 10 or so minutes talking about the irrigation systems. If we already have an irrigation system on the farm, we need to make sure that we maintain them really well. Some of the good practices is to fix the leaky parts, including the nozzles, the connectors, and any of the parts on the pivot. And we also have to pay attention to the pivot pressure regulators so that they're not worn out and everything is working perfectly. During the winter time, we should turn off the end guns of the pivot for maintenance. And in those drier places, it will be a good practice to apply some newer nozzles that can generate larger water droplet sizes in order to reduce evaporative loss. Because especially for those areas with windy and dry weather, the evaporation will be significant to lose water from the nozzle after the system is turned on. So having those newer nozzles will help to reduce evaporation. Right now, we have this new cutting edge technology for irrigation called the variable rate irrigation. This might be a futuristic system for increasing the irrigation system for not just potatoes, but also other types of crops. The idea of the variable rate irrigation is to apply varied rates of water along the length of the center pivot so that the application of irrigation can meet the site-specific water demand of the crops. So it covers the spatial variability instead of applying a flat rate across the whole field. The end goal of variable rate irrigation is to increase the crop yield and quality while reduce the unnecessary water loss so that we can increase the water productivity, which is calculated by the yield produced per water drop. And at the same time, if we can manage the water really well, there will be a reduction of leaching potential, and that will be associated with better water quality. However, I have to point out that variable rate irrigation will not reduce the crop evapotranspiration because ET is determined by the weather and the crop, not by the irrigation system. Right now, the high cost is still the hurdle for widespread adoption of variable rate irrigation. I'm gonna quickly talk about two VRI systems today. One is called the speed control, and the other is called the zone or nozzle control. So I have two graphs here to show the major difference between the speed control VRI and the zone or nozzle control VRI. Speed control VRI is much cheaper compared to the more fancy system. We can see that under the speed control VRI, the field is divided into different pie slice shape parts, where if this part of the field, this blue color part of the field, has more coarse textured soil or is higher in elevation, then that means it needs more water. The plants tend to have more water stress. So we need to slow down the speed of the center pivot when the center pivot reaches to this area, and then the crop will receive more water from the center pivot. Comparatively, if this red colored area of the field is lower in elevation or has more heavier soil texture, then it does not need that much water and is less susceptible to water stress. So when the pivot reaches to this point or reach this region, it can speed up a little bit and apply less water. So we can easily control the speed, the moving speed of the center pivot. Slowing down means more water application. Speeding up means less water application. And we can adjust that based on the specific need of the different sections within the field. But we have to make sure this is the zones under this speed control VRI is going to be pie slice shaped. A more newer, more innovative VRI system is called the zone or even nozzle control VRI. This one is way more costly compared to the speed control, but the growers will have more flexibility by using this fancier system. Under this system, either a batch of nozzles on the center pivot will be adjusted, or each individual nozzle will be adjusted based on the specific crop need in the field. So we can see this very highly colorful regions under on the map, meaning that the system has high flexibility to adjust the irrigation amount, and that will be based on the crop need, very specific in each area or on each spot. So in the year 2019, my research program did a field research on 2 commercial farms to evaluate the use of the nozzle control VRI versus the speed control VRI, and their effects on the potato yield, quality, and storability. So we worked with 2 farms. Farm 1 had the nozzle control VRI, the fancier version, and the second farm had the speed control VRI. On each field, we randomly pick an average spot, meaning the average spot means that this spot represents the most common field condition within that field. We also pick the highest spot within that field for elevation, and that means the plants grown in the higher elevation will be more susceptible to water stress. And then we pick a wet spot, the lowest spot of the field that tend to be waterlogged if there is a heavy rainfall. So we can compare the potato production or the potato growth under the average, the dry, or the wet areas of the field managed by a nozzle control VRI. Similar protocols were applied to the speed control VRI field, where we pick the average spot representing the most common field conditions, and we pick the highest spot that is called a dry area, and we pick a wet spot that is more prone to soil saturation. And we just want to compare the how potato can be produced under those different spots or regions managed of the field managed by different VRI system. So what we can see from the results is that under the nozzle control VRI, the yield from the wet spot was significantly lower than the yield from the average spot, and the yield from the driest or the highest spot is actually the highest. But there was no significant difference of yield between the dry and the average spot. Comparatively, there was no significant difference between the yield from the dry, average, or wet area of the field managed by the speed control VRI, but we have to pay attention to the fact that overall, the yield produced from the speed control VRI are lower than the yield produced under the nozzle control VRI. So this is the potato yield data. We also measured the nitrogen removed by tubers under those 2 different systems. This graph table here just shows the result from the nozzle control VRI. At harvest, we measured the total nitrogen amount in the tubers from the 3 spots that I just mentioned of the field. And we can see that there was no significant difference between the 3 spots when we were talking about the nitrogen removal by the tubers. However, the absolute value from the average spot was lower than those under the wet or the dry spots. We also measured the specific gravity of the two systems from this, under each system from the 3 spots. For the nozzle control VRI, there was a significant reduction of specific gravity in the wet area compared to the dry and the average area. For the speed control VRI, there was no significant difference between the 3 areas or 3 spots: dry, average, and wet. For tuber quality, we also measure the length to width ratio because these are Rossi Burbanks. The length to width ratio are going to be important for processing French fries. Again, we found that there was some significant difference under the nozzle control VRI, where the tubers from the wettest spot of the field tend to be more elongated or skinny than the tubers from the dry or average areas of the field. Similar observation was made from the field with the speed control VRI. And we can see that there was a significant difference of length to width ratio, that the wettest spot always produced the largest length to width ratio for both nozzle control and speed control VRI. For hollow hearts, we did not see any significant difference between the 3 spots for the incidence of hollow hearts, but there was a significant increase of hollow hearts under the wet spot from the speed control VRI field. These are some pictures that we took during storage. These tubers were from the wet spot of the field. We can see that there is a noticeable rotting problem with the tubers, which were from the wet spot. And this makes sense because if they're from the wet spot, meaning that there was more soil moisture, soil is wetter during the growing season, and that will cause enlarged lenticel, which will be a perfect entry point for infection of diseases during storage. So after we saw so many results, I think a good summary of the VRI system is that you have to be smart about using different VRI. And if you have a large wet area in a field, even with VRI, it will be hard to manage because the soil tend to be wet anyway. Sometimes if the season receives too much rainfall, then there will be a high chance for having rotting soil, even you have a VRI. But other than that, VRI is going to be helpful for people to manage a field with either elevation variation or soil type variation. Next, let's talk about some new technologies for irrigation system, some other new technologies for irrigation system. This one is called the dragging nozzle, a dragging tube, center pivot, where on the pivot, there will be a drip tube installed. And so that when the center pivot moves around the field, those tubes will be taken along the field, and then there will be some emitters on each tube that can apply water very specifically to the soil surface within the field. The flow at each drop will be controlled by the length or the number of emitters of the drip tubing when the center pivot is moving around the field. And in that case, the canopy can stay dry because the water is directly applied to the soil surface instead of the canopy. And so there will be a chance to reduce the disease and evaporation of water. With this system, the growers don't have to worry about foreign materials. Everything will be attached to the center pivot. And the irrigation efficiency will be as high as 95% compared to 60%, 60 to 65% of irrigation efficiency for the current conventional center pivot. And then the pivot rutting will be avoided because there will be always a dry wheel tracks under this system. However, the downside of this system is very high cost. Will be 20 to 25K dollars per pivot if using groundwater. And then during the winter time, if not stored appropriately, the animals will chew on the drip tubes or it will be damaged by the strong winds. This kind of system is specifically recommended for areas with very severe drought issues like California. This new system will be way more cost effective if that area for potato and other vegetable production is having some really bad drought. Next, we will be talking about the irrigation scheduling, and I will share a couple of different irrigation scheduling methods with you. The first common irrigation scheduling approach is the hand fill method, or it's called the subjective method, where you can just easily take a handful of soil, squeeze it in your palm, and then feel how wet or dry the soil is by referring to the USDA NRCS Program Aid number 1619. There is very detailed information in that brochure to tell you if you feel a certain level of resistance by squeezing, how much water is in that soil. This method is relatively accurate. It reached an accuracy of about 5%. And you can take the soil samples within the rooting zone with 1 foot increments. And you can check on that for 3 or more sites per field, just to have an average feeling about the soil moisture. In Wisconsin, this hand feel method is the most common one for our growers, just because they're more used to it. But the personnel who can do this hand feel method needs to be highly experienced with a lot of years of knowledge and experience, so they can be accurate to tell the soil moisture level. And on top of that, this method is going to be labor intensive and time consuming because the growers have to drive their pickup trucks to their fields and really feel the soil. This is a screenshot of the USDA brochure. The title of this brochure is Estimating Soil Moisture by Feel and Appearance. I encourage our audience to refer to this brochure. The second approach for irrigation scheduling is to refer to the daily crop water use, or in other words, it's called evapotranspiration, or ET. In this method, we can calculate the crop ET by multiplying the reference ET with the crop coefficient. The reference ET is calculated based on a reference crop, usually alfalfa. And this reference ET, the ET0, is a function of weather conditions, including solar radiation, daily temperature, wind speed, and relative humidity. And then we also need to know the crop coefficient, which is a function of the crop growth, in order to calculate the crop ET, the real crop ET. The reference crop ET0, usually is calculated by the Penman-Monteith equation or the Priestley-Taylor equation. And in our university, we have developed a irrigation scheduling program using the Priestley-Taylor equation to calculate the ET0. The major obstacle of using this ET method is to be accurate when we calculate or when we quantify the reference ET and the crop coefficient. If any of those two is inaccurate, we will have an inaccurate estimation of ET for the real crops, and that will cause either over or under irrigation. The third irrigation scheduling approach is to use the soil moisture probes so that it can indicate the soil water status to the growers. Currently, there are two major types of soil moisture sensors available on the market. One is to measure the volumetric water content, and the other major type is to measure the soil water tension. Some of the producers or manufacturers have a stick of sensors where they install one sensor at different soil depth. So when you insert the stick into the soil, there will be a series of sensors measuring the soil moisture at different depth. And then the very cutting edge technology can connect that information based on using cloud-based technology so that people can keep track of their soil moisture using their smartphone or tablets. The drawbacks of using soil moisture probes include that the moisture sensors can only be installed at specific locations within the field. So it does not blanket the variability, the spatial variability within the field. You cannot install thousands of soil moisture sensors within one field. That's just not possible. So everything will be very site specific and cannot tell you the status of the whole field. And the second downside is that this technology is also very labor and time intensive because we have to spend time installing and removing the moisture sensor in each year, just because we have the crop rotation. So you have to manage the installation and removal of the moisture sensors every year. The selection of soil moisture sensors will be based on a lot of different factors, including what type of crop you're growing, what is your soil type, what is a center pivot system you're using, if it's a center pivot or a linear move system, how much labor you have available, how durable you want the sensors to be, how much maintenance they need and you can provide, and then your financial budget. I can tell that the cheaper ones will be more hard to maintain and will likely give you more trouble to do the troubleshooting. The costly ones, once you install them in the field, it will be relatively easy to have them reliable and last for a long time. These three irrigation scheduling methods, the hand feel, the ET, and then the soil moisture, are very common ones, or kind of like the old school approaches. We also have some new technologies for irrigation scheduling, and that is to use the canopy temperature to indicate the water status of the plants. The underlying physiological mechanism of this idea is that when the crops are under some water deficit, they will close up their stomata. Their transpiration will reduce, and then the leaf or the canopy temperature will increase. I have two graphs here to indicate the open opening of the stomata and the closing of the stomata. So when it's closed, then there will be an increase of the leaf temperature, and that can indicate that the crop is responding to the water deficit. We can use this knowledge to guide our irrigation scheduling. Some researchers have designed a sensor to detect the canopy temperature, and they will install those sensors among them on the center pivot so that when the pivot moves around the field, the sensor can tell the canopy temperature all over the field, across the field. And then we can use this information to schedule irrigation. If the temperature is higher, then that may indicate the crops are under water stress, so you need to water more. So far, this technology has been applied to cotton, corn, and sorghum, and people found that they can produce equal or higher yield for those commodity crops. The biggest challenge of this technology is the background temperature. Sometimes it can cause some noises and inaccurate information. So this technology still has space to improve, and hopefully in the future it will have less problem with the noise, and it will be more cost effective for the growers who are interested. This figure just to show you how the camera or the sensor is mounted, and then how, when the center pivot moves around, how it can take pictures during the move. So I have a list of tables here just to show the major differences, similarity, advantages, and disadvantages of different irrigation scheduling approaches. So we can quickly summarize that the hand fill is very straightforward, easy to use, but it has very low cost, but it's highly labor intensive and requires many years of experience to be accurate. Referring to ET is also should be efficient because it's easy to apply. There will be sufficient robustness under a wide range of environmental conditions if we want to use the ET. But this ET method is less accurate than the soil moisture-based method. And sometimes if we have an inaccurate estimation of ET, then we can have some over or under irrigation issues. The soil moisture method is also easy to apply, accurate, and some of the cutting edge ones, the newer ones, have a very user-friendly interface that you can control remotely. However, the installation and removal of those sensors are going to be an issue, and it cannot cover the spatial variability within the field. For the newer technologies using the temperature of the canopy information, that's going to be more straightforward, way more straightforward to tell the growers the information that they need about the soil moisture level and the crop moisture level. Excuse me. It will be a promising technology. However, there are still some obstacles to overcome with this new technology, and hopefully it will be more user-friendly in the near future. So just as a summary to wrap up today's presentation, this is just a presentation. This is a summary for irrigation management. I said it's in Wisconsin, but it does not only apply to Wisconsin. It applies to all the potato production. So in order to manage the irrigation more sustainably, we have to make sure we apply the water in the right place with an efficient irrigation system. we have to make sure about how much to apply and when to apply the irrigation water by using the correct irrigation scheduling. We can well maintain our existing center pivot or linear move systems so that it can function well during the growing season, or we can use the variable rate irrigation or the drag tube irrigation system to increase our irrigation efficiency. For irrigation scheduling, traditionally they're hand fill using crop ET or using soil moisture probes for achieving the goal. But there's also some technologies that are new, innovative, and cutting edge to improve the ease and efficiency of the irrigation scheduling. So my conclusion point is that new technologies will be more and more seen and welcome by our potato growers and other industry people to adopt in the near future in order to achieve a better management of irrigation, but not just irrigation, the other facets of potato production. So with that, I would like to conclude for today's presentation, and thank you.